All right, today we are starting our last section of new material for the semester. Wow, can you believe it? Yeah, we're super close to being done. And we are taking a look at our last section about integers, specifically multiplication and division. We'll focus on multiplication today. And then there's some properties of multiplication that we'll look at, and then finish up next time, which is Monday. So for starters, we're going to take a look at a couple of models that you have seen before, namely the charged fields model, the CHIPS model, and the number line model, and see how it works with multiplication, because there are some variance things, kind of things that look a little bit different with this, in order to use it for multiplication. So let's start with this, and let me get a pen out, sorry. It requires a little bit of description in order to make this make sense. So here's the deal. The -4 and the -3, which could be switched, and that would be okay. One of them needs to represent the size of a group, and the other one how many groups, okay? So the way I'm going to write it is I'm going to call this that I have 4 groups, and this one says that they're of size 3. There's nothing special. I could say I have 3 groups of size 4. It doesn't matter. Just pick one. And also, one of them needs to say that you're removing, in particular, you're going to remove the 4 groups. And the size 3 is actually meaning that I have 3 negative chips, because there's a negative on the 3. Does that make sense to everybody? So one of the negatives means remove, the other negative means that I'm removing negative chips. That's what my 2 negatives mean, removing and chips that are negative. So when I start this problem, that makes it a little bit weird, because I don't have anything to start with. I'm supposed to be removing something, but there isn't anything to remove. I have nothing. So in order to remove, we talked about this last time with subtraction, and I was trying to say, remove 3 negative chips, but all you had in there were positive chips. How did we include chips that were negative so that our problem didn't actually change value? Do you remember? We put in what? A positive and a negative, and they're called what? 0 pairs. You got it. So what we're going to do to start with is that I need 0 pairs in here. And because you know enough math to know, does anybody have any idea how many negative, or not negative, but 0 pairs I need? I need 12. You're exactly right. Why 12? Yeah, because 4 times 3 is 12. Eventually I'm going to have to remove 12 negative chips. So I need 12 negative chips, which means I also need 12 positives. So we're going to go through and we're going to put in 12 positives and 12 negative chips. So before I do anything else, what number does this circle represent? I haven't heard it yet. It's 0. That's the number 0. Funny way to write it, but it is, because every 0 pair, every positive has a negative corresponding with it, so it's 0. So what are we doing? Well, it says that I need to remove 4 groups, and the groups need to have 3 negatives in them. So here's 3 negatives, and I can remove it. And here's 3 negatives, and I can remove that. And here's 3 negatives, and I can remove that. 3 negatives, and I can remove that. That is 4 groups of 3 negatives that I have removed. So what remains? 12 positive chips. Yup. And lo and behold, a negative times a negative equals a positive. Charge field model is just like a chip model, just uses pluses and minuses instead of blacks and reds. So if we're looking at the charged fields model, we operate with it exactly the same too. So I put in 0 pairs. If I put in 6 positives and 6 negatives, and I do it again, this is what I have. And we can remove sets of three negatives, specifically 4 sets of 3 negatives, which leaves me with 12 positives. All right, so that's good, right? Yeah, no problem. Number line model is awkward. I'm not going to lie. I find it to be very awkward. When you write it in terms of a word problem on your group work, when you get to that next time, you'll see a word problem, and it has a really great application. In fact, I'll mention it. But let me first just show you how the model works, and then I'll describe a word problem where it makes sense. But on the picture itself, I'm not a fan. So on my number line, so you're going to draw a number line, of course. And as you're taking a look at the number line, this is telling, the first number, again, you can switch the numbers, it doesn't matter, but this is telling you to move left. You might be saying, okay, well, that's good, right? I can move left because it's negative. So I'm moving left, and we're doing it 4 at a time. And I think also that makes sense, right? Move left 4 at a time. Fantastic. And the next part's the awkward part. And so I'm going to do it in terms of time, just because it's helpful to think about in the context of the actual word problem I'm going to describe in a minute. So this is at a time starting, we'll use 3 hours as our reference, 3 hours ago. You could use days, you could use years, I don't care, but some kind of time frame. So here's what I mean. We're going to move 4 to the left. Oops. Or move left 4 at a time. And we're going to do it 3 times. Okay, is everybody good so far? Moved left 3 times, and I did it in steps of 4. Or you might be familiar with the phrase skip counting. It's kind of like that. We're skip counting backwards. Okay, we're jumping 4 at a time backwards, and we're doing it 3 times. Okay, so here's the kicker. I end at 0. I always end at 0 in this method. And the answer to my question is where I started. So in particular, it's saying, what is this number right here? Where did I begin all this movement? And if I moved 4 at a time, 3 times, of course, I'd begin my movement at 12. So the answer then would be 12. So let me give you the context of the one that's in your book, which it makes sense in this description from a number line perspective. The example that they use, not example, but the problem that you're going to see is about a university whose enrollment is declining. And it says something like, at, whatever university, the enrollment has decreased 50 students a year for the last 4 years. How many more students were there 4 years ago than there are today? Can you see how that's describing this picture? I'm going down 50 at a time. How many did I start with before I started decreasing all this nonsense? What did we used to have? And that's how they describe it. And it does fit the number line perspective very well. All right, a few facts about integer multiplication, useful to know. Let A and B be integers. If A is less than 0 and B is less than 0, then one way to think about multiplication is to think about taking the absolute value of A times the absolute value of B. Okay. But that's only working, of course, because these are both what kind of numbers? Negatives. So if they're both negatives, you can kind of ignore the negatives and just take the positive part and you can multiply them together. That's one way to think about it. The second option here is that you have one negative and one positive. So if you think about it that way, one negative and one positive, then it's really just going to be the negative of the absolute value of A and the absolute value of B. It's kind of just a counting game. One negative, it stays negative. Two negatives, it becomes positive. Properties of integer multiplication. There's like almost nothing new here, maybe nothing new here for this particular one. These look just like the properties of whole numbers that we saw back in chapter 3, just like. So what did closure say? Yeah, good. That if I multiply A and B, this equals a unique integer. And unique is valuable, but the integer part's the important part. When I multiply integers, I get integers. When I multiply whole numbers, I get whole numbers. When I multiply, whatever the fill in the blank is, I get that kind of number back. Okay, so that's what closure means. The second one is the commutative property. So what does the commutative property say? Good, you can switch the orders that A times B is equal to B times A. Right, 5 times 2 is 2 times 5, always and forever. And it works with integers too. Negative 2 times 5 is 5 times negative 2. Associative property. In order to describe the associative property, I need 3 symbols. And it's all about the grouping of them, right? So if I group the first 2 together, it will be equivalent to having the 3 integers with the second 2 grouped together. And that's useful information because sometimes multiplication is easier in some steps to do things than in others. Okay? It's lots easier to continue using 8 times 5, which is 40, than 8 times 3, which is 24. Another one, identity property of multiplication. So this is the, if you shorten it, this is the multiplication or the multiplicative identity. You need the multiplication and you need the identity in order to make sense of that. Because what is the multiplicative identity? You're giving me the property. What's the identity element? 1. Yeah, it's the number 1. And this is the unique identity element such that, and tell me what you were talking about, Savannah. It's just the other way around. 1 times A equals A. The order of it doesn't matter. So the identity gives you back the element you started with, and it's commutative. The order doesn't make any difference. Yeah, good job. The distributive property. So I don't know why, but the distributive property is the one that we kind of fixate on. Like if you remember any property at all, for some reason, the distributive property seems to be one of the most common ones people remember. And what it does is it combines what you do when you have multiplication and addition going on. So I have A times B plus C. That's the same as AB plus AC. And it doesn't matter whether the A is at the beginning or the A is at the end. So if I had B plus C times A, if you want, you can write it as BA plus CA, but that's exactly the same thing. The order doesn't make any difference. All right, so what I want you to do, oh wait, sorry, one more, my bad. Zero multiplication property of integers. So this is actually talking about the number 0, and what do you know about when you what do you know happens when you multiply by the number 0? It equals 0. So 0 is the unique integer such that A times 0 equals 0 times A, which is what? 0. When I multiply by the identity, not identity, but the multiplicative 0, I get 0. All right. So we have 4 items And I'd like for you to try your hand at identifying which property goes with which. Once you've finished identifying what you believe your four answers are, check with the neighbor and see if you guys agree. Obviously not all 6 properties are present here since there's only 4 problems, okay? All right, what'd you get? What do you think that first one is? That's closure. Closure tells us that when I multiply 2 integers together, it's an element of the integers. That's the notation for that. What's the second property? That's the 0 property. What's my third one? Yep, distributive. And the last one, it's commutative. I know there was a little bit of discussion going on that. Is everybody good with that being commutative? All right, so that's where we're going to stop for today.